Inside a specialized vacuum chamber at NASA's Jet Propulsion Laboratory in Southern California, something happened this week that most people have not yet heard about, but everyone needs to understand. Engineers fired up an experimental engine that glowed white-hot at temperatures exceeding 5,000 degrees Fahrenheit. Its central tungsten electrode blazed brighter than molten lava. It ran on lithium metal vapor, and it reached power levels that no electric propulsion system in the United States has ever achieved before. 120 kilowatts, a record, a milestone, and the opening chapter of the most significant shift in how humanity travels through deep space since the invention of the rocket engine itself. NASA Administrator Jared Isaacman said it plainly after the test results were confirmed. He said that at NASA, they work on many things at once, and they have not lost sight of Mars. He said that the successful performance of this thruster demonstrates real progress towards sending an American astronaut to set foot on the Red Planet. He confirmed that this was the first time in the United States that an electric propulsion system had ever operated at power levels this high. The test took place on February 24, 2026, and the results were published by NASA's Jet Propulsion Laboratory just this week. What this test represents is not a distant concept or a theoretical paper. It is hardware. It worked. And it is pointing directly toward the engine technology that will carry human beings across the 140 million mile void between Earth and Mars. To understand why this matters so much, you first need to understand the problem that has stood between humanity and Mars for as long as engineers have been drawing up mission plans. The problem is not distance alone, it is time. With today's most advanced chemical rocket engines, the same fundamental technology that launched every spacecraft and every astronaut in history, a crewed mission to Mars and back would take somewhere between 2.5 and 3 years in total. The transit alone, each way, runs between 7 and 9 months depending on the planetary alignment. During those months, the crew is exposed to cosmic radiation at levels that significantly increase their cancer risk. They are living in microgravity that weakens their bones and muscles and affects their vision. They are consuming supplies at a rate that demands a spacecraft so massive with so much fuel and food and water that the cost of launching it becomes staggering. And if something goes catastrophically wrong on the way to Mars, a chemical propulsion spacecraft has essentially no ability to abort and return home at speed. The crew is committed the moment they leave Earth orbit. There's no fast way back. Nuclear propulsion destroys that problem. It does not chip away at it. It does not make modest improvements at the margins. It fundamentally changes the geometry of the mission. A spacecraft equipped with nuclear electric propulsion, powered by a megawatt-class nuclear reactor driving engines like the one just tested at JPL, can accelerate continuously during the transit, building up speed gradually but relentlessly, reaching Mars in as little as 4 months rather than 7 to 9. A spacecraft equipped with nuclear thermal propulsion, a different approach where a nuclear reactor heats hydrogen propellant to produce thrust directly, can cut transit times even further, operating at a specific impulse that is 2 to 3 times higher than the best chemical engines ever built. Shorter transit means less radiation exposure, less time in microgravity, less food and water required, a lighter vehicle, lower launch costs, and critically, a spacecraft with enough propulsive margin to abort and return to Earth if a life-threatening emergency occurs. Every single factor that makes a crewed Mars mission dangerous, expensive, or borderline impossible with chemical propulsion becomes manageable or solvable with nuclear propulsion. The specific engine tested at JPL belongs to the nuclear electric propulsion family. This technology, funded by NASA's Space Nuclear Propulsion Project, which began in 2020 at Marshall Space Flight Center in Huntsville, Alabama, works by using a nuclear reactor to generate electricity and using that electricity to drive electromagnetic thrusters. Those thrusters ionize a propellant, in this case lithium metal vapor, and accelerate the ions using powerful magnetic forces to produce thrust. The efficiency is extraordinary. Electric propulsion systems use up to 90% less propellant than traditional chemical rockets for the same amount of work. They do not produce a single explosive burst of thrust the way a rocket engine does. Instead, they push gently but continuously for days, weeks, and months, gradually accelerating a spacecraft to speeds that chemical engines could never sustain. NASA's current deep space missions already use solar-powered versions of this approach. The Psyche spacecraft, on its way to a metal-rich asteroid, uses electric thrusters running on solar power that will eventually accelerate it to 124,000 miles per hour. A nuclear-powered version of the same principle, running not on solar panels, but on a compact nuclear reactor that works equally well whether you are near the sun or in the outer. Solar system is the next step. And the JPL test just demonstrated it can work at the power levels a Mars mission actually needs. What makes the 120 kilowatt threshold significant is that it is a major step toward the megawatt-class capability that mission planners have identified as the minimum target for practical human Mars transportation. A single electric thruster cannot push a crewed Mars spacecraft by itself. The vehicle will need an array of thrusters, each running at high power, with a reactor providing the electricity to drive all of them simultaneously. The progression from current spacecraft thrusters, which typically run at kilowatts of power, to the 120 kilowatt level demonstrated at JPL, and eventually to a full megawatt system, follows the same development path that every propulsion technology in history has followed. Test at small scale, prove the physics, validate the materials, then scale up with confidence. The JPL test proved that a lithium-fueled electromagnetic thruster can survive the mechanical and thermal stress of operating at this power level. The tungsten electrode that glowed white-hot at 5,000 degrees Fahrenheit did not fail. The 5 ignition cycles completed without anomaly. The vacuum chamber, designed specifically to safely test engines that use metal vapor propellants at extreme conditions, held. That is what a milestone looks like in propulsion engineering. Running in parallel to the nuclear electric propulsion work at JPL, a separate and equally important program is advancing nuclear thermal propulsion, a technology with a different operating principle and different advantages. Where nuclear electric propulsion uses reactor-generated electricity to drive electromagnetic thrusters, nuclear thermal propulsion uses reactor heat directly. In a nuclear thermal rocket engine, liquid hydrogen is pumped through a nuclear fission reactor core where uranium atoms split and release enormous amounts of heat. That heat converts the hydrogen into a superheated gas that is then expanded through a rocket nozzle to produce thrust, exactly as a chemical engine does, but at temperatures and efficiencies that chemical combustion cannot approach. The specific impulse of a nuclear thermal engine is roughly 900 seconds compared to 450 seconds for the best hydrogen-oxygen chemical engines in existence. Specific impulse is the metric that measures how efficiently an engine uses its propellant. Double the specific impulse means double the fuel efficiency, and double the fuel efficiency on a mission as demanding as Mars, where every kilogram of propellant you do not need to carry is a kilogram of food, water, medical supplies, or scientific equipment you can bring instead, is not an incremental improvement. It is a transformation. In January 2025, General Atomics Electromagnetic Systems, working in collaboration with NASA, completed a series of critical fuel tests at Marshall Space Flight Center that pushed nuclear thermal propulsion closer to operational readiness. The test campaign used a facility called the Compact Fuel Element Environmental Test, CFET, which subjects reactor fuel samples to the exact temperature and chemical conditions they would experience inside a running nuclear rocket engine in space. The fuel samples were cycled through temperatures reaching 3,000 Kelvin, more than 5,000 degrees Fahrenheit, in the presence of hot hydrogen gas, the same propellant that flows through a nuclear thermal engine during operation. Each test cycle included a 20-minute hold at peak temperature to verify that the fuel material could sustain continuous operation without eroding or degrading. The fuel survived. In a non-hydrogen environment at General Atomics' own laboratory, the same fuel performed well at temperatures up to 3,000 Kelvin, confirming the performance that would enable a nuclear thermal system to run 2 to 3 times more efficiently than any chemical rocket engine in history. Scott Forney, the president of General Atomics Electromagnetic Systems, described it as a critical milestone in the demonstration of fuel design for nuclear thermal propulsion reactors. Dr. Christina Back, who leads the Nuclear Technologies Division at GAEMS, noted that, to the best of the team's knowledge, they were the first company to successfully test and demonstrate the survivability of nuclear thermal propulsion fuel in the CFET facility at NASA Marshall. The Draco program, demonstration rocket for agile cislunar operations, represents the most direct line from all of this, laboratory and ground testing to an actual nuclear engine operating in space. Draco is a joint effort between NASA and DARPA, the Defense Advanced Research Projects Agency, with a stated goal of demonstrating nuclear thermal propulsion in Earth orbit. NASA's Space Technology Mission Directorate is leading the development of the nuclear thermal engine itself, while DARPA is acting as the contracting authority for the full spacecraft stage. The target for the in-space demonstration is currently set for no earlier than 2027. If that demonstration succeeds, if a nuclear thermal engine ignites in Earth orbit for the first time and produces thrust, it will represent the first time any nation has operated a nuclear rocket engine in space since the Soviet Union's experimental Topaz systems decades ago. It will validate the ground test data. It will qualify the fuel, the reactor, and the engine system for the environment where they will actually be used. And it will clear the path for a flight-qualified nuclear propulsion system to be incorporated into the spacecraft architecture that will carry the first humans to Mars. The question of when that Mars mission actually flies is one that depends on many factors beyond propulsion. Technology, funding, political will, the Artemis lunar program's success, and the development of life support, habitat, and entry systems for the Martian surface. But the question of whether nuclear propulsion will be part of that mission has effectively been answered. NASA and DARPA have agreed on the Draco demonstration. Congress has sustained the Space Nuclear Propulsion Funding Program through multiple budget cycles. General Atomics and Standard Nuclear, which acquired Ultrasafe Nuclear. Technologies both received contract extensions in 2025. 3 separate industrial teams have been competing to develop the best reactor and engine designs since 2021. The institutional and financial commitment is real, and it is growing. The test at JPL this week is part of that same momentum. Proof that the nuclear electric propulsion track, which complements rather than competes with the nuclear thermal track, is also advancing on a timeline that matters. It is worth pausing for a moment on what the combination of these 2 nuclear propulsion technologies will eventually mean for how humanity relates to the rest of the solar system. Right now, Mars is a destination that requires years of preparation, billions of dollars of spacecraft mass, and acceptance of radiation and physiological risk at a level that has given mission planners serious pause for decades, with nuclear electric propulsion providing continuous thrust and nuclear thermal propulsion providing high thrust departure and arrival burns. A Mars mission changes from an expedition into an operation. The transit time compresses, the crew size can potentially grow, the supply requirements become manageable, the abort capability becomes real. Mars stops being the edge of the humanly possible and starts being the beginning of a regular route. And once Mars is on a regular route, the outer solar system, the moons of Jupiter, the rings of Saturn, the ocean worlds where scientists believe life might exist. Today comes into the range of human ambition rather than staying permanently beyond it. The geopolitical dimension of nuclear space propulsion cannot be ignored either, because the United States is not developing this technology in a vacuum. Russia and China both have active nuclear space propulsion programs. Russia's heritage in nuclear-powered spacecraft runs back decades. The Soviet Union flew nuclear reactors in space on military reconnaissance. Satellites throughout the Cold War. China's space nuclear ambitions have been publicly outlined in national space strategy documents, with Chinese researchers publishing detailed mission analyses for nuclear-propelled Mars missions in peer-reviewed journals. The country that achieves operational nuclear propulsion for deep space first does not just gain a technical advantage. It gains a structural advantage in every future mission to Mars, the asteroid belt and beyond, a faster, more capable transportation system that defines who can do what in deep space for generations. That competitive reality is part of why Draco exists, part of why NASA has sustained its space nuclear propulsion funding through budget pressures that canceled other programs, and part of why the JPL test results were published and publicized immediately, rather than sitting in a classified report. The United States is showing the work because the work is real and the stakes are planetary. The white-hot tungsten electrode inside JPL's vacuum chamber was not the end of a story. It was the beginning of one. Every test cycle, every successful fuel hold at 3,000 Kelvin, every kilowatt of power demonstrated in a lithium vapor thruster pushes the physics of human Mars travel from theory into engineering. The engineers who designed and built and fired these systems did not do it because Mars is theoretically interesting. They did it because Mars is reachable, because the technology to reach it exists, and because the only thing standing between a human being standing on the surface of another planet in the present moment is the relentless, undramatic work of proving hardware under the harshest conditions science can simulate. That work is happening now, and it is changing everything.